Welcome. My name is Dennis Erdogan and I am a PhD student at the Christian Doppler Laboratory for Innovative Control and Monitoring of Automotive Powertrain Systems. Today I'm going to present to you one of our research topics, control and interface design for engine and powertrain testing. Ever shorter development times and complex vehicle architectures require the testing of individual components on test beds. The independent development through test beds in hardware-in-the-loop configuration helps to reduce development time by enabling the parallel development of vehicle components. For example, an engine can be developed and tested on an engine testbed where the missing parts of a vehicle are simulated and the dynamometer tries to emulate the behavior of these missing parts such that the engine has the same loads than in the real world. Further advantages are reduced costs, reproducible tests, arbitrary environmental conditions, and measurements which are otherwise not possible to make. For example, the torque measurements of the half shafts of a powertrain. The accuracy of such tests are crucial, and for this controller and interface design of hardware-in-the-loop tests are essential. Therefore, the goal in this topic is to develop high dynamic control schemes, make proper choices of coupling modes in hardware-in-the-loop tests, and the interface design itself. But before we dive into the topics deeper, I first want to give a brief overview of the Christian Doppler Laboratory. The Christian Doppler Laboratory is a multiple year-long cooperation between the TU Wien and the AVL List GmbH in Graz under our laboratory head, Professor Christoph Amedner. The primary research directions are component models for state estimation, diagnosis and degradation mitigation, power hardware in the loop testing under real driving conditions, and predictive multi-level control and operating strategies. In this presentation, I want to give an overview on power hardware in the loop testing, and I want to show some of the results which we achieved with our industrial partner. The research focus is first of all the design of high dynamic control schemes, for example, shaft or speed control on engine and powertrain testbeds. This is done because if the load machines are not able to reproduce the behavior which is given by the simulation fast enough, an error will occur that accumulates. For sophisticated control schemes, accurate models are necessary. Therefore, another research focus is the modeling of testbeds. In case of engine testbeds, the idea is to use gray box system identification, where the physical structure of the system is given and the corresponding parameters are estimated. The chosen structure here is a free mass model. For the performance of hardware-in-the-loop tests, another important point is the hardware-in-the-loop interface design itself. Here, the focus is on the improvement of hardware-in-the-loop coupling modes between simulation and the real world, and the design of new coupling modes. In the next few slides, I want to show you some of our achievements. Here on this slide, I want to show a system identification of engine testbeds. The motivation behind this is that a good model is necessary for well-designed controllers and hardware-in-the-loop interfaces. In this case, we chose gray box system identification with a free mass model because a lot of information is already available. For example, the inertias and some of the stiffnesses. The input to the systems, or to excite the system, is the dynamometer torque, and the outputs, so the measurements in this case, are the speed of the dyno, the speed of the engine, and the shaft torque, which can also be measured. The biggest issue here, or the biggest challenge, is the unknown combustion torque, which is influencing the quality of the measurements. To model the engine torque, Ansatzfunctions are introduced, and they are defined as follows. They are functions of the crankshaft position phi, and their shape is essentially determined by the factors k+. The normalized torque progression over 2 rounds is depicted in the graph. The black line shows the Ansatzfunctions t+, and the red one t-, and combined the turquoise line is obtained. The key idea is to only change the weighting theta to represent an arbitrary combustion torque progression. This graph here demonstrates how well the torque can be represented. The black line shows the measured torque of a diesel engine, and the blue line are the fitted Ansatzfunction. The deviations in the center are caused by the gas exchange, and overall a good fit can be achieved. The approach for accounting for the combustion torque that affects the system identification is to embed the unknown engine torque into the identification procedure. The system can be represented by a linear state space system with C denoting the engine torque. By extending the input vector with the Ansatzfunctions, the engine torque also becomes part of the system identification, with the parameter vector theta now additionally estimated by the gray box system identification. On this slide, the results of the identification are shown without the use of Ansatzfunctions. The upper plot shows the measured shaft torque in gray and the model output in blue. The diagram below shows the excitation signal via the dynamometer torque. It can clearly be seen that the periodic oscillations cannot be explained by the model. So here in this case, there is, for a short period of time, there is a constant dynamometer torque, and the oscillations here are only caused by the engine torque, which is not modeled in this case. Also, some other dynamics are also estimated badly, which you can see here, where these small oscillations are modeled quite badly. So now let's take a look at the results with the usage of the Ansatzfunctions. Here you can see that first of all, those oscillations here, which are purely induced by the engine torque, and also you can see that now these faster dynamics, these small oscillations, can also be modeled better by the parameter estimation. On the next 2 slides, I want to present a high dynamic engine testbed speed control. Engines cause a lot of oscillations in the speed signals, as you can, for example, see down here in this plot, where the black line is the dynamometer speed over time and the red line is the engine speeds over time. And this makes it very hard to control for conventional controllers, because they tend to feed back those oscillations, and it might lead to additional loads to the engine by those conventional strategies. An idea how to solve this is the so-called 2-degree of freedom control. This separates the disturbance response from the reference response of a controller. Most of the time, flatness-based feed-forward controllers are used for this purpose, but they struggle in some situations. So therefore, we are representing a 2-degree of freedom control with a model predictive feed-forward controller, which produces optimal feed-forward trajectories for the input and for the output. Down here, you can see the block diagram of such a control scheme. So you have the model predictive feed-forward controller, which also is able to consider constraints and delivers optimal input signal, feed-forward input signals to the speed controller. So the actual fast reference response is done by the model predictive feed-forward controller, and the PI controller only steps in if there are deviations between the wanted speed and the actual speed. On this slide, some results are shown. On the left-hand side, we see a conventional state space controller, a state feedback controller, and on the right-hand side, we see a true degree of freedom control in combination with a model predictive feed-forward controller. So on the upper plots, we see a step response from 1000 RPM to 1250 RPM, with the black line showing the reference and the turquoise line the actual engine speed. As you can see, there are a lot of oscillations in this engine speed, and this is caused by the engine itself. And ideally, the feedback controller would just simply ignore that. On the plots below, we see the input signal, which is the dynamometer torque. And yeah, as you can see here, they are oscillating quite a lot. So, and here on the right-hand side, we additionally have these optimal reference trajectories, which are given by the model predictive feed-forward controller. And you can see not only is it faster than just a pure state feedback controller, at the same time, the input signal is almost not oscillating at all. I also want to show you a big step response from 2000 RPM to 3000 RPM, where you can see the input signal is hitting the constraint of 530 Newton meters. And you can see that the step of 1000 RPM can be reached within 100 milliseconds, and therefore the controller can be considered as very high dynamic. If you're interested in any of these topics presented today, or feel like you could benefit from a cooperation with us, please do not hesitate to contact us for further information. Many of the topics presented here have already been published. Please also find links to our publications on our website. Thank you for your attention.